Hello. In this video, we're going to go over the monotone convergence theorem. Before I get to the idea of the monotone convergence theorem, what it is and how we can prove that, let me talk a little bit about why we need such a theorem. Why do we need the monotone convergence theorem? So if you think about the convergent sequences, in order to prove a sequence AN converges, you need to find some limit a and then prove that an minus a is less than epsilon. For any given epsilon, after a point positive epsilon, after a point the difference between an and a is less than epsilon. Of course, the difficulty of this is that sometimes the limit may not be possible to find, or we may not know what the limit is. So the question is, can we find a way to prove a sequence converges? Can we show a sequence converges without having to find its limit? And the monotone convergence theorem partially answers that question. We will talk about this question towards the end of the course when we talk about Cauchy sequences. So what is the monotone convergence theorem? In order to be able to state the monotone convergence theorem, we need to know the definition of an increasing and a decreasing sequence. And this is something that you have seen in I believe pre-calculus. So a sequence an is called increasing if an is less than or equal to an plus 1. So every term is less than or equal to the next term for all positive integers n. It is called decreasing if every term is greater than or equal to the next term. We say it is monotone if it is either increasing or decreasing. That's called monotone. We say it is strictly, so if I just add strictly to the definition, to the wording, if I add strictly increasing, then I would have to drop the equality sign. So strictly increasing means every term is strictly less than the next term. Strictly decreasing means every term is more than the next term. And strictly monotone means either strictly increasing or strictly decreasing. Okay, so in this theorem, which is called the monotone convergence theorem, we will prove that monotone sequences converge if and only if they are bounded. Okay, so here is the proof. So the statement of the theorem is if and only if. One direction is fairly clear, and that is the forward direction. If a sequence converges, we know it is bounded, and that's something we have proved before. So the forward direction is, since this is true for every sequence, every convergent sequence is bounded, we are done. So if you take a convergent sequence, it's bounded. Therefore, monotone convergent sequences are also bounded. So that direction is easy. For the backwards direction, we're going to in fact prove the parts A and B of this theorem, which is to say, if an is increasing, then the limit is the supremum. And if an is decreasing, then the limit is infimum. As usual, we're going to talk about the idea of the proof first, and then we will get to the proof itself. So let's assume that an is increasing. So let's assume an is increasing. And the decreasing portion would be very similar. So if an is increasing, there's a supremum because we know it is a bounded sequence. So assume an is increasing and bounded. So in any case, since it is bounded, it has a supremum. So by the completeness axiom, I'm going to call that S. S equals supremum of AN exists. And when I write down supremum of AN, this means supremum of this set A1, A2, etc. It means that supremum of that set. Okay, so the supremum exists because the set is bounded. Now we're gonna show that in fact AN approaches supremum. So if you look at the supremum, which I called S, we know that the terms are gonna get close to S. What we want to show is that we want to show AN minus S is less than epsilon. Since it is supremum, AN is always less than S. So it won't be to the right of S. It's always going to be less than S. However, because it's the supremum, if I take S minus epsilon, some term in the sequence would be more than S minus epsilon. But because it's increasing, every later term would be in between AN and S, which is essentially what we wanted. So now we're going to turn that into a formal proof. Let epsilon be positive. Since S minus epsilon is not an upper bound for A1, A2, etc., there is some natural number n such that AN is more than S minus epsilon. So this means let me write it down here. Suppose n is greater than or equal to n. If you look at AN minus S, this would be S minus AN, because S is a supremum, which is going to be less than S minus. Now, AN is less than A capital N, which is less than epsilon. This is less than or equal to. So I'm going to write down the reasoning here. This is because S is the supremum of AN. This one is because AN is greater than or equal to AN because it is increasing, and this one follows from here. So that means AN minus S is less than epsilon, which means limit of AN is in fact S as n approaches infinity. So AN converges to S. So this proves the part A of this theorem. This proves A. Now for B, you would have to do something quite similar. So I won't write down the proof of this one. Proof of B is similar. So all you would have to do is, instead of doing S minus epsilon, you will do S plus epsilon. But the proof is nearly identical. Okay, so that was interesting. So now we have a tool that shows a sequence as long as it is monotone, is convergent. And the only thing we need to check is if the sequence is bounded. The nice thing about this theorem is that it's an if and only if statement, so it's biconditional. So if you want to show a monotone sequence is convergent, the only thing you need to show is that it is bounded. If you want to show it is divergent, you need to show it is unbounded. Okay, so we're going to use that idea to solve a few examples. First example, show that the sequence 1 plus 1 over 2 plus 1 over 3, etc. diverges. If you write down a few terms of this sequence, you see that they are getting larger and larger. However, it's not very easy to pinpoint the growth. It doesn't grow that fast. And in fact, the growth of this sequence is like natural log. But that's something we will prove later. So let's see if we can prove this is in fact unbounded. So note that an plus 1 is greater than or equal to an. And this doesn't even have to be part of the solution. So this would be kind of like the scratch work which I will put on this side. So if this is the case, then in order to show it is divergent, we need to show it is unbounded. Okay, so now how do we do that? If you look at a1 is just 1. a2 would be 1 plus 1 half. Now, of course, finding a formula for an isn't really possible, but we can approximate these ans and show that they are actually quite large. For example, if you look at a3, if you look at a4, you would get 1 plus 1 half plus 1/3 plus 1/4. What I'm going to do is I'm going to replace these two by 1/4. So this gives me 1 plus, this is 1 half, and this is also 1 half, so that's 2 halves. A8 would be A4 plus 1/5, 1/6, 1/7, and 1/8, which is more than, A4 is more than 1 plus 2 halves, and this is more than 4 1/8, which is 1 plus 3 halves. And if you do something similar, A16 becomes A8 plus 1/9 all the way to 1 over 16. That's greater than 1 plus 3 halves, that's A8, and then 8 1/16, which is 1 plus 4 halves. So kind of see the idea. Now, we don't even have to include this as part of our official solution, because we will have to prove something more general. So in fact, what I'm going to do is I'm going to put that inside my scratch work. This will be also part of the scratch work, and we will start the official solution below this. So here is now the solution. So what we're going to do is, by induction on n, we will show a sub 2 to the n is more than 1 plus n over 2. So basis step, or equal to, because of the first case, because of the step 1. Basis step a2 equals 1 plus 1 half, which shows that the basis step is true. Inductive step, assume a sub 2 to the n is more than or equal to 1 plus n over 2. Then we're going to look at the next one. A sub 2 to the n plus 1 is equal to a sub 2 to the n plus 1 over 2 to the n plus 1, 1 over 2 to the n plus 2, all the way to 1 over 2 to the n plus 1. This is greater than or equal to, by inductive hypothesis, we have 1 plus n over 2 here, and these are 2 to the power of n plus 1 minus 2 to the power of n terms. Each one of them is more than 2 to the power 1 over 2 to the power of n plus 1. And this simplifies to 2 to the power of n plus 1 minus 2 to the power of n is 2 to the power of n over 2 to the power of n plus 1, which is 1 plus n plus 1 over 2. So this means a sub 2 to the power of n plus 1 is greater than or equal to 1 plus n plus 1 over 2. Now, we will show that an does not converge. And how do we do that? We show that an is unbounded. Note that if C is some real number, then you can make this one more than C, or rather perhaps the one that we already had here. We're going to make sure that this is more than C. And how can we do that? We could just multiply both sides by 2 and subtract 2. We get 2C minus 2. So as soon as you do that, you know that A sub 2 to the power of n is more than C. So then, by the Archimedean property, there is some integer n such that n is more than 2C minus 2. So that means if I look at A sub 2 to the n, that's 1 plus n over 2, which is greater than C. And therefore, the sequence an is an unbounded sequence. And thus it diverges. So that's the first example on monotone convergence theorem. Now, a somewhat of a better example would be the next example, and also a very useful example. So c to the power of n approaches 0 if c is between -1 and 1. Okay, so if you look at this example, c to the power of n, when c is between -1 and 1, the behavior is a little bit different if c is between 0 and 1 and if c is less than 0. For example, if c is 1/2, the sequence is 1/2, 1/4, 1/8, etc. That is if c is 1/2. But if c is -1/2, then it is not quite decreasing or increasing. It is oscillating. So it becomes larger, then it becomes smaller, then it becomes larger, but its absolute value becomes smaller. So what we are going to do is we're going to have to take two cases. So first, suppose c is greater than or equal to 0. If you look at the next term, the n plus first term of the sequence, this is c to the n times c, which is greater than or equal to c to the n times 1. I'm sorry, less than or equal to c to the n times 1. And since c is less than 1, thus cn is decreasing. So we have a decreasing sequence. So now that we have a decreasing sequence, what we can do is we can say that it does have a limit. So by also we know that it is bounded. So note that c to the n is between 0 and 1. Thus, and it's also not 1, but it doesn't really matter. C to the n is a monotone bounded sequence. Now, since it is a monotone and bounded sequence, by the monotone convergence theorem, c to the n converges. So let's assume that the limit is some s. So suppose the limit of c to the n is s. We know that it has a limit, so now we have to find the limit. So bear with me here. One thing that we know is that c to the n approaches c, but this is a kind of common strategy that we use. Since c to the n approaches s, c to the n plus 1 also approaches the same thing. So because c to the n plus 1 is a subsequence of c to the n, and that means limit of c to the n plus 1 is also the same thing. Now if you look at the limit of c to the n plus 1 as n approaches infinity, we can take one of the c's out, so we get c times limit of c to the n as n approaches infinity. This is c times limit of c to the n is s, so this means s is equal to cs, which means s times 1 minus c equals 0. But s was between -1 and 1. It was not 1, so that means s is 0. So this tells us that the limit of cn is in fact 0 as n approaches infinity. So what did we do? Intuitively, here's kind of the idea. If you look at the sequence c, c squared, c cubed, c to the fourth, etc., this approaches s. If you multiply it by c, it's basically the same sequence. The first term is dropped, but it should approach cs. So therefore c times s is the same as s, and that gives us s must be 0. So the limit is 0. This was when c is non-negative. So now assume that c is negative, and of course greater than -1. If you look at the limit, if you look at the sequence c to the n, absolute value of c to the n minus 0 is the same as absolute value of c to the n minus 0. So why did I write it down like this? Because then I can get this in the form of the comparison lemma. It just gives me 1 absolute value of c to the power of n minus 0 by what we proved above. Absolute value of c to the n approaches 0. So that tells us by the comparison lemma, limit of c to the n is in fact 0. As n approaches 0, infinity is in fact 0. So this completes the proof of this theorem. Okay, so we're going to move on to the next theorem. So this is also an application of the completeness axiom. It follows from the example that we did above. Okay, so first, what is this theorem, or I guess lemma? And next, how do we prove it? This one is called the ratio lemma for sequences. So what does it tell us? It tells us, let's say you have a sequence Cn, and the ratio of the consecutive terms of the sequence approaches a number L. In other words, if you look at Cn plus 1 over Cn, this is roughly a number L. And this L is either a real number or it is infinity. If L is more than 1, then Cn is unbounded and therefore it diverges. And if L is less than 1, then Cn converges, and it converges to 0. Okay, so we are going to prove this theorem. Let me first of all tell you why this would have to be true. If the ratio of the terms is roughly L, then each of the terms is gonna have to be the first term times L to the power of n minus 1, roughly speaking. It's because it's basically a geometric series, a geometric sequence. Now, we know what happens to a geometric sequence. The geometric sequence approaches either 0 if the common ratio is less than 1, and it approaches infinity if the common ratio is more than 1. If the common ratio is 1, since this is an approximation, we can't really decide which one it would be. It could be either. I'm going to prove the second part of this theorem, and then the first part would be quite similar idea. So I'm going to present the proof for part B of this theorem. If L is less than 1, then Cn converges to 0. So how do we do that? What I want to do is I want to first, as usual, give you the idea of the proof. So I have the limit is L and 1 is here. So I would like to show that in fact the ratio stays here, stays small, stays less than 1. And in order to do that, what we're going to have to do is to take some epsilon. So what epsilon do we take to avoid 1? If you think about this, is you would like to be not close to 1. So you could take the distance between 1 and L and then divide it by 2. We know 1 is more than L, therefore 1 minus L over 2 is positive. So let epsilon be 1 minus L over 2 in the definition of limit. So if you let that in the definition of limit, what you're going to end up getting is there is some natural number n such that for every natural number n, if n is greater than or equal to n, then Cn plus 1 over Cn minus L, the distance between these two, is less than epsilon that we took. Now let's see what happens. So this tells us absolute value of Cn plus 1 over Cn is less than L plus 1 minus L over 2, which is 1 plus L over 2. Now, note that 1 plus L over 2 is less than 1 plus 1 over 2, which is 1. So this tells us Cn plus 1 over Cn is less than 1 plus L over 2. So if you write these inequalities starting from capital N, so C capital N plus 1 over Cn is less than or equal to 1 plus L over 2. C capital N plus 2 over Cn plus 1 is less than or equal to 1 plus L over 2. And in fact, we don't have equality sign, although it doesn't really matter. And if you write it down all the way to Cn plus 1 over Cn less than 1 plus L over 2, or perhaps the one right before that, what you're going to end up getting is, after multiplying these fractions, you are going to get C capital N from the first one and Cn from the last one. This would be less than 1 plus L over 2 raised to the power of, there are n minus n terms here. This is for all n greater than n. Now let's see what happens. What we get is Cn is less than C capital N 1 plus L over 2 to the power of negative capital N 1 plus L over 2 to the power of n. Now this is going to be a constant, and this is for all n greater than n. Now this portion, if we write it down like this, we get exactly the comparison lemma. So since 1 plus L over 2 is less than 1, 1 plus L over 2 to the power of n approaches 0. And of course 1 plus L over 2 is positive. 1 plus L over 2 to the power of n approaches 0. By the comparison lemma, Cn approaches 0 as desired. So this proves the second part of this theorem. The first part has a similar idea. It's quite similar. However, what you need to do is you need to show the other direction, on the other side. You need to show Cn is more than something, but it's a similar idea. You need to take your epsilon to be L minus 1 over 2 and then work it on the other side. Okay. And as I said, when L is 1, the ratio lemma for sequences is inconclusive. So for example, if you take Cn equals n, this diverges, and the ratio Cn plus 1 over Cn is n plus 1 over n, which is 1 plus 1 over n, that approaches 1. So the ratio approaches 1, but the sequence diverges. If you take Cn equals 1 over n, this converges. And if you take Cn plus 1 over Cn, you would get n over n plus 1, which also approaches 1. So the limit is 1, the limit of the ratio is 1, but the sequence in one case it diverges and in the other case converges. Okay, so one last example and then we are done with the discussion of monotone convergence theorem. Let an be a sequence of real numbers satisfying this. Prove that an converges and find its limit. If you write down a few terms, as usual, we're going to write down the scratch work on the right, and then we'll turn that into a rigorous solution. So the first term is 0. The next term, if you plug in 0, you get 1/4. The next term, if you plug in 1/4, you get 1/16 plus 1/4. If you write down a few more of these terms, you will see this is 5 over 16. You will see that you get 5 over 16 squared plus 1/4. And it isn't difficult to see that this is in fact getting larger and larger. 5/16 is less than 5/16 squared plus 1 over 4. Not difficult to see why. Now, in order for us to prove that in fact this sequence is convergent, what we would have to do is we would have to show that the sequence is increasing and the sequence is bounded. So first, how do we show that the sequence is in fact increasing? So we would like to show an plus 1 is greater than or perhaps equal to an. Let's rewrite that and see what we get. Okay, so this is actually quite familiar. This is a perfect score. This is an and then minus a half squared. So this is clearly true because of the trivial inequality. Okay, so that's the first thing. It's an increasing sequence. We will show an is increasing. An plus 1 minus an is an squared plus 1/4 minus an, which is an minus a half squared, which is greater than or equal to 0. Thus, an plus 1 is greater than or equal to an. The next thing we need to show, now that we showed that it's an increasing sequence, we need to show it is bounded. Clearly, every term is greater than or equal to the first term because it's an increasing sequence. Now we have to show it there is an upper bound. So how do we show there's an upper bound? So I would like to show an is less than or equal to something. Since we are dealing with recursions, it might be a good idea to use induction, because what is the idea of recursion? The idea of recursion is every term is given based on the previous terms. The idea of induction and recursion are pretty much the same. Induction is also basing something on the previous assumptions. So if I start with this, I would, and of course I know that an is non-negative, an squared plus 1/4, which is an plus 1. I would like this to be less than or equal to m. But I know this is m squared plus 1/4. This is less than or equal to m squared plus 1/4. So if I can show this, then I'm done. So I need some m that satisfies this, and I also need m to be positive. And by inspection, you can see, for example, 1/2 works. So we're going to claim that an is less than 1/2 for all n. We prove this by induction. Basis step is clear. A1 is 0, which is less than 1/2. Inductive step. For the inductive step, suppose an is less than 1/2 for some n. An plus 1, and of course I will also show that they are positive, so that's greater than or equal to 0. Suppose this is the case. An plus 1, which is an squared plus 1/2, is going to be less than 1/4, plus 1/4, plus 1/4, which is 1/2, and an plus 1 is of course positive. So this completes the proof. Therefore, by the Monotone Convergence Theorem, limit of an exists. So let's say limit of an equals a exists. So now we know that an plus 1 equals an squared plus 1/4. We're going to take this and we're going to take the limit of both sides. Limit of an plus 1 is going to be limit of an squared plus 1/4 as n approaches infinity. Since an plus 1 is a subsequence of an plus 1 also approaches to the same number. Therefore, a equals a squared plus 1/4. And if you solve that, you end up getting a equals 1/2. And this came from this equality. So if you take this equality, you can conclude this by taking the limit. On the left we get a, on the right we get a squared plus 1/2. Thus, limit of an is in fact 1/2 as n goes to infinity. So this brings me to the end of this video. So today we talked about the Monotone Convergence Theorem, and we did some examples on that. Okay, so if you would like to continue with this course, feel free to subscribe. I will see you in the next video.